Hey guys, we're going to do a quick video here on topic 5.1 for Handout 2. So, in our first example here, you are asked to estimate the magnitude of the drift speed in a wire that carries a current of 1 amp. You're given the radius and the number of electrons per unit volume, and that number is important for getting an answer here. So, without overcomplicating it, you just take that number n, 10 to the 28 meters electrons per meter, and plug it into this equation. Okay, so that gives us our number of electrons. All right, once you have done that, your math will look something like this. You'll notice here that this is actually division. I've taken the current 1 amp and then I've divided it by this quantity by using the -1 exponent you see here. Okay, so I kind of have a habit of doing this just because it looks neater on one line, I feel. But if you find it confusing, you could always just rearrange it and put, you could put that on there and make it a fraction. That's fine either way. All right, the final answer is 5 times 10 to the -5 meters per second. And then that is the magnitude of our drift speed. Okay, yeah, note that you could have calculated the area first. I didn't do that. I just plugged it right into the equation. So, but not a bad idea to break your calculations apart in that way. Okay, you were then asked to hypothesize why, in view of this very low drift speed of electrons, the lights are going to turn on instantaneously. And the reason for that is just because the electric field through the conductor propagates at close to the speed of light in vacuum. It would actually be the speed of light through copper in this case, but it's still a very, very high speed. Okay, so for 5.7, you have electric current flowing in a conductor, and our conductor changes its diameter. And here we have an example of something that's kind of similar to fluid dynamics, actually. If you guys go on to study more physics, you'll see problems like this in relation to pressure and velocity and stuff like that. So anyway, we don't need to worry about that here. So how do we handle this? Well, we need to think about this in terms of proportionality, as happens a lot in physics. So we have our drift velocity equal to current divided by number of particles times area, cross-sectional area of the conductor, times the charge of the particle, which in this case is the fundamental charge of an electron. Okay, the key bit here though is that drift velocity is going to be inversely proportionate to cross-sectional area. And what we also know is that area A is less than area B. I've identified these two areas on here. And, when in doubt, draw a diagram. It's never a bad idea. So as the cross-sectional area of a conductor increases, the drift speed will decrease. And because you were asked to both state and explain what's happening here, that would be 1 mark. So this is your statement. The second mark would be for your explanation, which is because drift speed is inversely proportionate to the area of the conductor. So if you're doing an exam and you're asked to state and explain something, you should have 2 points, and they should be 2 separate points. So statement, explanation, 2 marks, done. Okay, 5.8, the work done in moving a charge of 2.0 microcoulombs between 2 points in an electric field, blah, 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 blah. Very simple application of your data booklet formula. Potential difference is equal to work done divided by charge of the particle. So there you go. Just plug it in. You'll get 75 volts. One thing you want to be careful here is when you're plugging in, I guess we could call them complex fractions, where your denominator is composed of multiple terms. You want to make sure that in your calculator you put a parentheses around that. You guys probably already know this, but just throwing that out there. All right, 5.9, determine the speed of a proton that is accelerated from rest by a potential difference of 5.0 times 10 to the 3 volts. So first thing we need to recognize is that work done is equal to potential energy. Did I skip B here? I apparently did. Well, it's in your book, so let's not get too worked up about it. So work done is equal to kinetic energy, and work done, here we combine a couple of data booklet equations. Work done is equal to potential difference times the charge of the particle, and we get that just from this formula. Okay, so we're rearranging that very slightly into this new and special formula. Okay, so work done is energy, so we just equate kinetic energy to the work done, and we're good to go. And then it's a simple matter of doing a little bit of algebra. If you ever need me to break down the algebra, please don't hesitate to ask. I'm happy to do it. It's not a pain. I just take some shortcuts here because it's faster. If you need the help, definitely advocate for yourself. Let me know. All right, we then plug in our values, and you will get 9.79 times 10 to the 5th meters per second. So really, guys, this is the tricky bit, this equating work done and kinetic energy. From there, it's fairly straightforward algebra. Okay, again, part B for 5.9, I'm going to have to go back and add it to this PDF, but it is in your book, so again, there you go. All right, so 14A, how much charge flows through a lamp in 1 second if the current is 0.25 amps? Again, just a very straightforward rearranging of this equation where current is equal to the change in charge divided by the change in time. We solve for change in charge, and we plug in our values, and we get 0.25 coulombs. Right, for part B involves an equation that is not in your data booklet, and it's really useful. So I'm going to skip over here to the equation because you really should know this. So change in charge is going to be equal to n, where n is the number of particles. And E is the fundamental charge. Okay, so the fundamental charge is in your data booklet. It is the charge of an electron or a proton. An electron obviously has a negative charge. Proton has a positive charge. Okay, there you go. So keep that in mind. Anyway, once you know that, then again, it's just a matter of some very simple algebra to rearrange the equation so that we now have the number of particles, and you will get this nice convenient answer, 1.6 times 10 to the 18 electrons. Okay, 15. How much charge is passed through a battery in 1 hour if the current is 120 milliamps? Okay, so we need to convert the current to amps, not milliamps. So that is what this step does. Just dividing the current given by 1,000, and that will give you amperes. Okay, the change in time is 3,600 seconds for 1 hour. Pretty important value. Anyway, we then rearrange the equation for current in the data booklet. Delta Q is equal to current times change in time. Plug in our values, we get 432 coulombs, which is quite a lot of charge. We then look at part B, how long will it take for a total charge of 100 coulombs to flow through the battery. And here we just rearrange our equation again. And we get change in time is equal to the change in charge divided by current. 830 seconds is your answer. Okay, 22A. The density of copper is given there. It's 8,960 kilograms per cubic meter. And its molar mass is 63.5 grams. Okay, so the tricky part here, and chemistry students may be familiar with this, the number of moles, N, is equal to N divided by Na, where N is the mass, and N sub A is the molar mass, okay? So I did have to convert that molar mass, 63.5 grams, into kilograms, but you can see that there. Okay, and this is going to give me then 1.41 times 10 to the 5 moles. And note that this is not the same as the number of particles, which we're going to look at here in a second. Okay, the number of particles is going to be given by multiplying that previous value by Avogadro's number. And again, chemistry students should be pretty familiar with this bit as well. Once we do that, we will find that we have 8.49 times 10 to the 28 atoms, and that will give us 8.49 times 10 to the 28 electrons, but that is assuming that we have a 1-to-1 ratio of electrons to atoms, and that is not always the case for metal ions, so you want to be a little bit careful there. And in fact, most ions of copper, I believe, have more than one electron per atom, one free electron per atom. So just be aware. All right, 24. How much energy is transferred when 4.7 coulombs of charge pass through a power supply rated at 110 volts? Okay, so here we just, again, take that equation we had previously. I'm using E for work done, but it's the same equation, so don't get excited. Okay, so energy is equal to voltage times charge, and we plug in the values from the problem. We get 517 joules. It looks like that should actually probably be 520 if we're going to give it the appropriate number of significant figures, but whatever, the book says 517 joules, so we'll go with that. Okay, how much charge must flow through the supply in order to transfer 1.0 megajoules of energy? Again, rearranging same equation, plug in the values, we get 9.1 times 10 to the 3 coulombs. Okay, part C, last one. We're asked to find how many electrons are needed to transfer 1.0 megajoules of energy. So the number of electrons is going to equal the total charge divided by the charge of one electron. Again, that is the same equation we used previously. It's that one. Okay, I'm not using the fundamental charge here because, well, I probably should be actually. Yeah, let's change that. Why not? Okay, so let's, consistency is important. You are now the fundamental charge. There you go. Okay, so anyway, we plug in our values again, and we get 5.7 times 10 to the 22 electrons. Ta-da! Okay, last, determine the speed of a proton that is accelerated from rest by a potential difference of 5.0 times 10 to the 3 volts. Yeah, you know, I'm not quite sure why I included this. Okay, you know what? I'm just going to drop this here and maybe chat about it a little later. But yeah, if you have any questions, just look over the solution. It looks like, yeah, it appears I skipped ahead a little bit. So I'm going to rework this as well. Okay, guys, any questions? Don't hesitate to let me know. And we'll chat soon. All right, take care.